Thanks. I will begin with a word of prayer. Heavenly Father, we thank you for this time we have just to meet together and study your creation. Thank you for all the wonderful things you do for us every day, Lord. In your name I pray. Amen. Okay, so today I'm going to talk to you guys about the calculus of smooth operators. Now, that's actually not entirely true in the sense that I'm not really being that general. Mostly, I'm actually going to talk to you about the calculus of constant coefficient differential operators. So, let me talk about what I mean. So, here's the definition basically. If you have t, all right, and it's some kind of mapping from, let's say, f to f, all right, where this funny-looking f is a function space, some sort of space of functions. So, for example, well, anyway, then t is called an operator. All right. So an operator is something that takes in a function and gives you back a function. All right. Now, our principal interest, right? We're mostly interested in the following application. At least for the moment, we're going to let these functions be usually smooth functions on the reals. So these are real functions. Basically, you're looking at f from R to R, right? I guess I should say R comma R for the moment. Functions from R to R with lots of derivatives, okay? Many derivatives as you like. Although, truthfully, I also want to look at the case that the function space is take the domain to be reals, but the range can be complexes, right? So here it would be something like f equals u plus iv, where u and v are smooth on R. Sorry, this is just a lot of, you guys probably would call it jargon. But this is our context, all right? I want to look at operators that take in a real valued function and spit out a real valued function, or they take in a complex valued function of a real variable and return to you another complex valued function of a real variable. In fact, I'm really not being at all that general, so I mean, I'm probably wasting my time saying these things at the moment, but our typical example is just what? We are mostly interested in t equal to DEqns, all right? Or you could write it, we'll just write that also as big D, all right? So big D is differentiation. So that's understood to either be DEx or DDT as appropriate to the context, right? So that's our typical example. Of course, what is it, if you feed a function to the differentiation operator, what happens? Right, take f, you feed it to the differentiation operator, what does it give you? It gives you df dx, right? Another function. And that's also true in the complex domain, right? So if I have u plus iv, we talked about this last time, differentiation takes me to du dx plus I times dv dx, right? Again, a new, smooth, complex valued function. Okay, so that's what we're going to study here, operators. Really, we're just studying just two kinds of operators and how to combine them. The one is the differentiation operator. The other one is even more sort of basic. The other example we look at is the so-called multiplication operator. Multiplication by, let's say, C. All right, so here's the way this works. This is really hold on, watch this, guys. So C operates on F, all right? And what's it give you back? just what, CF, right? It's just a multiple of f. Now, to be picky, what I mean by this, right, to define this precisely, I should tell you this. I should say CF parentheses of x is equal to c times f of x for x in the domain, for x in the reals. All right. So point-wise, you define a function. So technically, to define an operator, I have to do something like that. But sometimes we just write c operating on f. It gives a CF, yeah.
Unless I'm mistaken, we've pretty much been using operators, like all functions are operators of this sort, right? It goes from a constant to a constant, but a constant function to a constant function.
Yeah, so Luke is basically saying, hey, this is nothing new. Very good. That's true. We're just giving a language to things we've already done. That is exactly what I'd like you to think. What else can you do with these operators? New operators from old, how can you do it? New from old, if I have t and if I have s operators, right? And c a constant, then you can define new operators. For example, you can talk about t, plus or minus s. How would you do that? How does this operator work? And so here's the rule. We usually write square brackets for like the function input. That's just a common notation. I may at times slip up and use round brackets there, but the square brackets is to like emphasize, hey, we're looking at an operator. All right. So this is defined to be, right, t of f plus or minus s of f. So that's how you add operators. You add them pointwise. What's a scalar multiple of an operator? This is like entirely unsurprising here. That's c times t of f, okay? So this is how you add them. This is how you multiply them by a scalar. Now for finally, I'm going to say something that's a little bit non-obvious. How do you multiply operators? What's multiplication for operators? Anybody know? You know. Do you know? No? Okay. I couldn't tell. Well, I'll tell you. So the way we multiply operators, t times s, what that means, right, when that acts on a function, is t of s of f. So multiplication is composition. Right? And in that light, we define powers of an operator. So from this, we get powers. So for example, like t squared acting on f, what's that mean? That means t of f. Or if you want, I can recursively define t to the n of f equal to t of t to the n minus 1 of f for any natural number. And if you want, we can take the 0th power to be the so-called identity operator. What's the identity operator? Just takes the function and sends it to itself. The identity operator is also the same as just scalar multiplication by 1. Okay, so this, I say calculus of smooth operators, but that's not entirely honest. What I should really tell you I'm doing is what? Let's be more honest here. We're really talking about the algebra at the moment anyway. But that algebra of smooth operators is actually going to allow us to solve the calculus of a rather large class of differential equations. So be patient with me. This takes about a half hour for me to like build up. But once I build up this machine, we will solve like so many problems it'll be disgusting how many problems we solve with this. Just utterly disgusting. So, but I need to warn you some dangers. All right, so let's try out this notation here for some specific example. So here's my example. Let's look at t equals to x squared times the differentiation operator. And let's let s just equal to the differentiation operator. So what's that mean? T acting on, for example, y would be x squared times dy dx. If you want me to be more pedantic, I could write, no, I'm not going to. You guys are engineers, you're not math majors, so this makes sense to you. All right. On the other hand, of course, s of f, s of y is what? Just dy dx, right? So let's calculate. What's s composed with t? Acting on y, what's that give us? That gives us s of t of y, right? Which is what? Well, s was what? S was d, right? That gives us the derivative. T of y is x squared times dy dx, which you could write as y prime if you like. I'll just write it as dy dx for the moment. I guess to be more explicit, let me say that that's really d dx of this, right? Well, we face a product rule, right? And so that gives us 2x dy dx plus x squared d squared y dx squared. Now, I'm in search of an operator equation. So what I want to do is I want to rewrite that in terms of, the same sort of, I guess I have introduced a new idea here, right? Multiplication by x squared. We talked about multiplication by constant. There I'm using like multiplication by x squared. Well, I don't know what that is. I guess I don't need to give it a name. Anyway, I want to, let me just get to the point. This is 2xd, right, plus x squared d squared. All of that acting on y. All right? Let's contrast that with ts. What happens when we calculate ts of y? So t of s of y, which is equal to, what was t? T was x squared d dx, right? S of y was dy dx. Yay, no product rule this time around, but we do have twice differentiation of y. Rewrite this a little bit. Got yourself x squared d squared, that operator acting on y. So you guys can compare, right? Check it out. This one versus that one. Now, by the way, this calculation we just did holds for arbitrary y, right? So if you have a calculation for arbitrary functions, that allows you to extract from that an operator equation. The operator equation we've just derived is that st minus ts is equal to what? I could look at it this way. We have st is equal to that. We have ts is equal to this. So if I take their difference, what do I get? 2xd, right? In other words, the so-called Lie bracket is equal to 2xd. This is called a Lie bracket. Now, that's not something I require you guys to know or anything, but the set of derivations forms what's called a Lie algebra. There's a lot more math to do here, but the bottom line is for us is that st is not equal to ts, right? Operators do not commute, generally speaking. For example, these. Okay. Mostly I'm doing this just for us to get used to the idea of multiplication of operators being composition and just the notation. You guys starting to be comfortable with this? Okay, so what's the relevance of this to differential equations? Right? let me show you why this is relevant to differential equations before I go on with my building of the machine. So our goal, basically, all right, is to unravel the nth order constant coefficient problem. So what is the nth order constant coefficient ODE? So basically, you're given constants, let's say A0, A1, AN minus 1, all right? And I'm going to write it this way. So what you're looking at is the nth derivative of y plus A sub n minus 1, the n minus 1th derivative of y. Let me get a marker that works better. The second coefficient, A2, y prime prime, plus A1, y prime, plus A0 times y, equals to 0. Very greedy. I want to solve this problem for arbitrary coefficients. This is our goal. We're going to find out it's actually really easy to do that. But to do that is tantamount, really, to understanding what differential operator. I can rewrite this. See, this is really d to the n, right, plus an minus 1 d to the n minus 1 power plus a2d squared plus a1d plus multiplication by the constant a0. That's the operator. And we're feeding it y, and we're supposing it's equal to 0. So I usually call this thing L, just to give it a name. Basically, our differential equation is the same as looking for how can we make L of y be 0. So if we can understand how to manipulate the algebra of this operator, well then we can learn something about the differential equation, right? Okay, so fortunately, there's no x's or t's in this, right? Like it's just powers of the differentiation operator and multiplication operator. And there's a couple really, really simple lemmas that govern the algebra here. So I'll show you. So lemma, that was supposed to be a lemma. Lemma 1 is that if I do multiplication by c times d to the any power, it's equal to the any power of the differentiation times the constant multiple. What's the proof of this? All right, watch this, guys. It's really, really complicated. C, the nth derivative, acting on a function f. Well, we know from calculus that that's what? Excuse me. This is CD, CD, and so forth all the way down, right? Anyway, the point is we can pull C out, right? So fine. Let me do this like a civilized human being. I would point out to you, first of all, that we have that C times D, F, right, is equal to C times dF. So you can pull this constant out from one time, right? And then if you look at 2 times, CD times CD squared times F, what is that? So I can pull that C out. Right? And then I can pull the constant out of that again by calculus. So that's C squared, D squared F. C squared, oh, I'm an idiot. What am I doing? I'm stupid. I don't want CD squared. I mean, this is, oh, fine. I guess I just proved something else. I'm sorry, guys. Okay, so this implies what? This implies C parentheses D to the n power, continuing down this line, is equal to C to the n D to the n, okay? That's actually useful to us. Let me just record this, lemma 1 and C to the n CD to, I'm sorry, I'm an idiot. CD to the n is equal to, curses. All right. I knew this would happen. I wasn't saying anything wrong, but I'm making a mess of things. We fix it. This is what I'm trying to prove. So what? So I do what? I have C, the nth derivative of f, right? By definition, that is C times the nth derivative of f. That's the multiplication, right? That's the definition of composition with multiplication. And then this, by properties of calculus, is the same as the nth derivative of C times f, right? Which, by the way, is the same as d to the n times the C operator acting on f. But this holds for arbitrary f. So that is C d to the n is equal to d to the n to C times C. All right. Sorry. My point was you can pull the constant out of the n-fold differentiation, all right? All right, lemma 2. Here it goes. D plus A times D plus B, all right, is equal to D squared plus parentheses A plus B times D plus AB. This is an operator equation. So how do you prove it? Pretty simple. We do D plus A times D plus B. We act on a function. Let's call it Y, because my Y's are prettier than my F's. And then, it's not a very good reason, but it's a reason. So this is D plus A, parentheses, of D plus B acting on Y. What's D plus B of Y? That is, I'm going to write it as Y prime, right? Plus B times Y. Then what does it mean, D plus A on this? That is D on Y prime plus BY plus A acting on Y prime plus BY. How does A act on Y prime plus BY? It just multiplies, right? So this guy gives us Y prime prime plus, pull the B out by lemma 1, or just calculus, whatever floats your boat, by prime plus ay prime plus aby. Tilt head, squint, we have it. So this is d squared plus a plus, well, b plus a finally. Find b plus a, d plus ab acting on y. But of course, a plus b is b plus a, and there you have it. So all I'm saying is the ordinary calculus says that you can multiply these operators as if they're polynomials. So the rules of manipulating constant coefficient differential operators is the same as the rules of manipulating polynomials. This is factoring, right? So like, I mean, we can extrapolate from, I mean, I think that's pretty much all I need. Trying to think. There's probably something else I'm forgetting. I know I need these two. I think that's enough, yeah. Oh, okay. Okay, so then from this, what do we get? So here's basically the theorem. If, you know, L is equal to d to the n plus a to the n minus 1, d to the n minus 1, plus a2d squared, right? And let me kind of unpack it a little bit here. Suppose you have a corresponding polynomial, right? Suppose p of x maybe x is a bad choice. Let's use p of lambda. Suppose p of lambda is equal to lambda to the n plus a to the n minus 1, lambda to the n minus 1, plus da da da, plus a2 lambda squared, plus a1 lambda, plus a naught. So in other words, I'm supposing that p of lambda, it's the same pattern, it's basically the same polynomial, except instead of being p of d, it's p of lambda, right? You could think of this as being quote unquote p of d, whereas this is p of lambda, if that makes sense, right? Right, if you have that, and further you have that p of lambda is equal to, you know, excuse me, lambda minus lambda 1, lambda minus lambda 2, lambda minus lambda n, all right? Then p of, well then L is also equal to d minus lambda 1, d minus lambda 2, d minus lambda n. In other words, if you can factor the polynomial p, you can also factor the operator L in this way. Now, of course, for a polynomial with real coefficients, it may or may not be the case that we have all real factors. We could have a complex, we can have like complex factors, and they have to come in conjugate pairs, right? Because our coefficients, if the coefficients of the polynomial are real. I am assuming, of course, that these are real numbers, right? So given that those are real numbers, this is a polynomial with real coefficients, you know that it has to have n complex zeros. And some of those might be real, but if they are complex zeros, they come in conjugate pairs, right? So there's a very well-known algebraic structure there. We studied it before in your algebra class, or somewhere. Okay, so this is essentially given to us by just application of these lemmas, all right? Now, what's that have to do with solving the differential equation? All right, fair enough. Good question. So what kind of, let's fundamental lemma. Lemma was, where were we out here? Lemma 3? I feel like we're on lemma 3. Is that right? I did too. It's 3. Check this out. If L is equal to L1, L2, dot, 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 LK, where L sub I, right, are linear operators. What does it mean for it to be a linear operator? Here, I'll let you in on the secret. A linear operator just means that, like L sub I of y1 plus y2, excuse me, c1y1 plus c2y2, if you get c1 L of y1 plus c2 L of y2, if you have that condition on the operator, it's called a linear operator. For example, multiplication operator and differentiation operator, both linear operators. Good news, the sum and difference of linear operators is again a linear operator. And also, the composition of a linear operator is again a linear operator. In other words, these guys, linear operators. Now, the critical thing about a linear operator is basically, from all this, you can show that L of 0, well, basically, sorry, there's an I here. L sub I of 0 is equal to 0. So linear operators send 0 to 0. All right? So suppose you've got this operator L, it's factored into k linear operators, and we have something else. And suppose that we have LK is LK of y is equal to 0, right? Then L of y is what? And then L of y is in fact equal to 0. Why is that? So L of y is equal to L1 of L2 dot 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 of Lk of y, right? Stupid notation. I guess I should write Lk minus 1 for the sake you see what I'm doing. Now what's Lk of y? This is, by assumption, 0, right? So what happens when you feed 0 to Lk minus 1? Well, it's a linear operator, right? So that's 0. And then the one outside it, 0, and 0, and 0, which is 0 all the way down. So proof by sound effect. There you go. 0. So lemma 4, if L is equal to L1, L2, dot dot dot, Lk, and if you have the Li, Lj is equal to Lj, Li for all ij, oops, sorry, forbidden math jargon, for all 1 less than or equal to I comma j less than or equal to k, right? In other words, if you have factored your operator into k commuting factors, right? Then if we have L, if we have Li of y equals to 0 for any I, for any, specific choice of I, let's say for some I, then L of y is equal to 0. See, because if it commutes, you can just move the L sub I. If they commute, right, here's the proof. So we have L of y, L1, L2, da da da, Li, Lk. If it commutes, I can just bring the I out to the inside. Right, so that's 0 by assumption, and then by the previous lemma, by the same argument as the last time, 0 to 0 to 0 to 0 to 0, it works out to 0 because you have 0 and 0 and 0 and 0 and 0. So, the fact that linear operators send zeros to 0, very, very useful. The fact that the operators we're looking at are commuting, how do I know they're commuting? How do I know that, so these guys right here, guys, are going to, this is going to be our L1, so to speak. This is going to be our L2, stuff like this, all right? I'm not imposing that notation universally. I'm just saying, conceptually, that's the kind of thing we're doing. There's a little bit more wrinkles than that, but that's essentially the idea. Why do those commute? It's implicit within lemma 2, right? Because the factor, you tell me x squared plus 2x plus 3 is, x squared plus 3x plus 2 is x plus 3 times x plus 1. And I say, no, it's x plus 1 times x plus 3. Which one of us is right? We're both right. You can factor polynomials either way, right? In the same way that polynomials, these operators can be factored either way, which is to say that these operators, these L sub 1 through L sub n's commute. Constant coefficient, the operators from constant coefficient, ODEs, are commuting operators, commuting linear operators. All right. Okay. I'm eventually going to get to the point. I told you it was going to take a few minutes to build the machine. We're almost there, though. What lemma am I on? Lemma 5. D minus lambda on y equals to 0 has solution y equals to e to the lambda x. Proof. D minus lambda, you feed it the exponential function. What's this? This is the derivative of the exponential function. minus lambda times the exponential function by the definition of that notation.
Is that lambda x or 2x?
Lambda. Everything's lambda. There's no 2's here. You're like, but lambda is written like this, not like this. That's true, but this is hardwired into my brain. I can't undo it. Sorry about that. If you notice that, very good. Not many people notice until I put it out. By the time I realized I was writing it wrong, it was too late. So anyway, the point is, of course, that is 0, or if you're from some parts of the world, 0. I used to have a friend from Calcutta, Tapomoy Guhar Sarkar. And for fun, I would ask him to say windshield wiper. He's like, you're a very bad person. I was like, what? Come on, say it. He's like, fine, windshield viper. I was like, thank you. I miss Tapomoy. Anyway, so, I didn't tell you. For lambda what? Lambda where? Element of what? See what we proved last time, or you proved in your homework, is we can put a C here. Works for real constants, works for complex constants, just the same. It's pretty awesome. All right, lemma 6. I'm going to be pretty greedy this time. D minus lambda to the n power acting on y equal to 0 has solutions y equals to e to the lambda x, x e to the lambda x, x to the n minus 1 e to the lambda x. I'm going to use induction to prove this. Many of you have had Math 250? No? Taking it? Yes? Anyway, you should know what induction is. Let me show you. What is induction? I mean, induction is, first of all, does it work for n equals 1? N equals 1, true by what? Lemma 5, right? The n equals 1 case was lemma 5. So then, inductively, suppose it's true for n. Yep.
You mean to have x each to the lambda x or lambda?
X. So it's true for some n in the natural numbers, okay? Consider d minus lambda to the n plus 1. Now, first of all, it's already clear, right, that this on y is equal to what? This is equal to d minus lambda, right, times d minus lambda to the n acting on y, right? And so from that formula and the induction hypothesis, what do I have? I'm already given that d minus lambda to the n y has solutions is equal to 0 for what? E to the lambda x, x e to the lambda x, right? All the way out to what? X to the n minus 1 e to the lambda x, right? That's the induction hypothesis. So if that's 0, right, it follows that the n plus 1th power also kills these things, because when you feed any of these guys into that, you get 0, but 0 maps to 0 under this linear operator. So it's already clear from that I have these n solutions. The exponential, x times the exponential, all the way out to x to the n minus 1 times the exponential. The only thing that remains for me to really look at is the next one, right? Why is it that d minus lambda to the n plus 1 y, what's the new one? X to the n times e to the lambda x. Why is that a solution to this? So again, that's d minus lambda times what? the derivative acting on x to the n e to the lambda x, right? Minus lambda acting on x to the n e to the lambda x. So what's the what happens with the derivative? Well, that's a product rule, right? So here we get n x to the n minus 1 e to the lambda x, right? Plus x to the n e to the, well, excuse me, x to the n lambda e to the lambda x by the chain rule, right? Minus lambda x to the n e to the lambda x. Oh, but check it out. So the last two terms are exactly the same, but with off by minus, so they cancel. So these guys are gone. And we got this, right? But what's that? That's x to the n minus 1 e to the lambda x. What do we already know from the induction hypothesis? That's one of the solutions of d minus lambda. I mean, fine, if you, well, oh, shnikes. I've forgotten something very important, which is what? You guys look confused. You should look confused. What have I very importantly neglected to write there? My bad. Oh, man. I wrote it in the step above, right here. So this, I'm missing the nth power, right? So this, I looked at this one down here. I looked at d minus lambda to the n times d minus lambda. Up here, it was convenient for my purposes to look at d minus lambda times this, just to emphasize that, hey, when you put y, any of these guys, right? Any of these guys fed into this inner operator are 0, hence it's 0, which goes to show, of course, that those are solutions. But then the second calculation, again, those cancel, and then I know that x to the n minus 1 times e lambda x is 0 when you feed it to this by the induction hypothesis. I can pull out the n, right? So there it is. So we've shown that if it's true for n, it's true for n plus 1. Therefore, by proof by mathematical induction, lemma 6 is true. Some of you don't look entirely convinced. Let me show you how this works out for the n equals 2 case. So if I like d minus lambda squared, first of all, if I have e to the lambda x, what do I get? For the same reasons that we went through in the n equals 1 case, the lemma 5, was it lemma 5? Yeah. This is d minus lambda times what? I mean, operating on 0, right? Which gives you 0, because the derivative of 0 is 0. Lambda times 0, 0. Now what happens when I look at d minus lambda squared acting on x e to the lambda x? The calculation I'm about to do is pretty much the same as the induction proof that I just did, honestly. So I have d on x e to the lambda x, right? The derivative of this minus lambda times that. For the derivative, I have the product rule, so I get e to the lambda x plus x lambda e to the lambda x. These cancel. See? These guys cancel. And that gives you d minus lambda times e to lambda operating on e to lambda x, which is 0. And there you have it. Yes, Luke? Something is askew.
I'm processing.
Oh, okay. That's cool. But my point is...
CPU 100%.
Oh, okay. CPU 100%. The point is that basically it's the product rule. It creates a term that cancels with the one that comes from the minus lambda, and it leaves you with something with 1 less power of x. which is automatically 0 because of the previous calculation. And that also works in the induction proof. Same animal. So one more lemma and we can solve this thing. Lemma 7, if L is a smooth, real differential operator, then L of u plus iv equal to 0 implies that L of u equals to 0 and L of v is equal to 0. Let me put that in other words. That is, if L of z is equal to 0, then the real part of z and the imaginary part of z are both real valued solutions. Somebody take a picture just now? Oh, that's weird. I think that book, like, it somehow caught a reflection of the sun because there's like a flash in my eye. That's weird. This last one you guys don't understand yet, all right? Let me show you an example of it. So example. So how about if I have d squared plus 1, right? What's this equal to? This is d, well, I'll tell you what, I'll just keep it like that. Let's look at d squared plus 1 acting on y equals to 0. I will show you, if we let y equals to e to the ix, right? Then what does this give us? What's y prime prime? What's d squared acting on y equal to? So each differentiation pulls down an I, right? So that gives you a what? Sorry, let me just get to the point here. That's I squared e to the ix, right? What's I squared? Minus 1, right? Which is just what, by the way? If y equals to e to the ix, that's equal to, this is minus y, right? So therefore, d squared y plus y equals to 0, or if you like, d squared plus 1 acting on y equal to 0. Which is to show you e to the ix is a solution to d squared plus 1 times y equal to 0, right? What kind of solution is it, though? Let me put this in words. Y equal to e to the ix is a complex solution to y prime prime plus y equal to 0. We're really interested in here in finding real valued solutions. So this doesn't quite suit our purposes, but lemma 7 tells us what we need to do. It's very simple. So there's a formula, Euler's formula, says that e to the ix, by definition essentially, is cosine of x plus I sine of x. Okay, so the real part of e to the ix is cosine. the imaginary part of e to the ix, it's sine. The I does not go into the imaginary part. It's the coefficient of I that's the imaginary part. Just like with numbers. If I have 2 plus 3i, what's the imaginary part? The imaginary part's 3. So anyway, this tells me that I have y1 equals to cosine x, and I have y2 equals to sine of x. These are both real solutions to y prime prime plus y equals to 0, which of course is interchangeable with this differential operator, right? Where's this e to the ix coming from? Do you guys understand why I did e to the ix there? Where's e to the ix coming from d squared plus 1? What'd you say? Nobody said anything? Can you guys factor d squared plus 1? I'll do the easy part. Lambda squared plus 1, we could write as lambda plus I times lambda minus I, right? Complex factoring. So d squared plus 1 is really d plus I times d minus I. And you see d minus I, right, acting on y equals to 0. Well, I know from lemma 5 that this is lambda equals to I. So y equals to e to the ix solves it. That's why I knew to try that. You're like, well, but what about the other factor, right? Like, what about the d plus I? What would d plus I suggest to you? If we look at this, what's that give us? That gives us lambda equals to minus I, y equals to e to the minus ix. Solves that one, right? And consequently, it solves, I mean, remember this, so this factors, right? So if you make either factor 0, it makes the whole thing 0, when you, right? Because these are commuting factors. So if it forces any one of them to be 0, the whole thing is 0. So either e to the ix or e to the minus ix will both serve as solutions. But it seems like there should just be two solutions, right? You guys have seen for a first order problem, one solution, right? Why is that? Because there's one, if you have a differential equation which basically specifies the conditions of slopes of functions, right? If you pick an initial position and you know the slope going forward, you can continue, right? So one initial condition fixes a solution for a first order problem. For a second order problem, you need two initial conditions. Like, you know from physics, you need an initial position and initial velocity, right? So you kind of expect that there should be two constants in the solution for a second order problem. And correspondingly, there should be like sort of two independent kind of solutions. So the fact that we got cosine and sine, and these are different things, although I'm saying that somewhat heuristically at the moment, it suggests that that should be enough. So like, what's in this e to the minus ix? Like, is there anything, what's there? Well, check it out. I mean, this is just what? This is cosine of x minus I sine x, right? So from this, we get like y1 equals to cosine x, the real part, or y2 equals to, well, I guess you could say minus sine x, but what's the difference? I mean, sine x, cosine, I mean, minus sine x, they're essentially the same solution. So, in fact, that brings me to lemma 8. Right? And lemma 8 is simply this. If you have L of yi equals to 0, for I equals to 1, 2, n, then L of c1y1 plus c2y2 plus plus cnyn is equal to 0, provided L is linear operator. For example, the constant coefficient differential equation, the one I just erased up at the top there, is such an L. So, this lemma 8 says that if I've got cosine and sine as solutions, I can form another solution, lots of other solutions, right? From lemma 8, this says that if I let y equals to like c1 cosine of x plus c2 sine of x, this is also a solution for arbitrary choices of c1 and c2. That's a solution to y prime prime plus y equals to 0. All right, the machine is almost conscious at this point. Let us bring it to life. 15 minutes, woohoo. Did I say half hour? Slightly off. All right, so some examples. So basically, this is the procedure for solving an nth order problem. You write it as an operator, all right? You factor the operator, and for each factor, you write down a solution. You add those together, that's the general solution. So here's one. Suppose I've got y prime 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 plus 3y prime prime plus 3y prime plus y equals to 0. In other words, d cubed plus 3d squared plus 3d plus 1, right? Hey, but everybody knows that that's d plus 1 what? You should realize by now, I don't lecture to make you comfortable. I lecture to try to make you learn things, right? Such is my style. But this is what? What? Cube, right, yeah, exactly. So I just go back to lemma 6, if I counted right. So we've got basically d minus a minus 1 cubed, right? So I know that I have y equals to e to the minus x e to the minus x squared e to the minus x. Those are all solutions, right? And consequently, my general solution is c1 e to the minus x plus c2 x e to the minus x plus c3 x squared e to the minus x. That's the general solution to this problem. All right, so, excuse me. How about this one? The fourth derivative of y minus 81 y equals to 0. So look at this. This is d to the fourth minus 81 times y. I can factor d squared minus 9 times d squared plus 9. Can I factor that? I can, right? That's d minus 3 times d plus 3 times d squared plus 9. I should probably create a lemma 9 for our convenience, but maybe I'll get to it next time. I don't know. I've enough lemmas for today. The point is, this tells us we get an e to the 3x. From this, I see I get an e to the minus 3x. From this, I see that I get a cosine 3x.